Okay, lecture 3 for set theory and logic. Look at the title. This is called Cartesian products. And this is a fairly simple concept. Okay. I am going to write here let A and B be sets. Okay? The Cartesian product that word Cartesian comes from the word the name of René Descartes. Okay? So the Cartesian product of A with B, okay, which we write this way, A and then an X, B. This is sometimes also called the cross product of A with B. Okay, so what is it? It is the set of all ordered pairs of first element from A let me not use the word element here because I don't want to misuse it. So let's say first entry from A and second entry from B. Okay? Do you know what an ordered pair is? You are used to writing down points on a graph, right? Like 0.25. That's an ordered pair. It's an ordered pair of the numbers 2 and 5. Okay, that's different than this ordered pair. You know that, right? A point on the graph 2, 5 is very different than the point 5, 2, right? That's why the word ordered is there. Okay? It's a pair of numbers, and which order you write them in makes a difference. That's what an ordered pair is. Okay? So let's write this now using set theory symbols. Okay, we write A cross B equals the set of all ordered pairs A comma B such that the first entry A is from the set A and the second entry B is from the set B. That is the Cartesian product of A with B. The Cartesian product of B with A is something different, isn't it? The Cartesian product of B with A would be the set of all ordered pairs where B comes first and then A. Okay? Now, you can certainly have a cross product of a set with itself. I said cross product, did you hear that? That's just normal for me, but I'll try to use the word Cartesian product. You can certainly do the Cartesian product of a set with itself. In fact, you guys are used to that. When you graph things, here, let's look at this. Let's draw an X and Y axis here. What are you used to that plane being called from calculus and stuff like that? Aren't you used to that plane being called R2, right? It's the two-dimensional real plane. What does every element of that look like? It looks like a point, doesn't it? In other words, every element of the plane is an ordered pair, isn't it? And the first entry is a what? It's a real number. And what's the second entry? It's also a real number. So what's that tell us? R2 is simply, well, here, let's write it down. It's the set of all ordered pairs, x, y, such that x is a real number and y is a real number. In other words, r squared is simply the Cartesian product of r with itself. Okay? Now let's do a little bit of practice with different areas inside that Cartesian product. Okay? What if I asked you this? Shade this set in the Cartesian product of r with itself, and then I'm going to give you a set. Let's do the set of all ordered pairs such that, let's say, x is an element of the closed interval from 2 to 4, and y is an element of the closed interval from 1 to 3. Let's shade that set inside of r cross r. Okay? What would it look like? Let's put some markings on our axes here. So x is between or equal to 2 to 4. So that means in between there. But also there's a restriction on y. Y is between or equal to 1 to 3. So what do we get when we put those together? We get a rectangle, don't we? Which is actually a square. Okay. Let's do another one. Let's do shade this set. The set of all ordered pairs x, y such that x squared plus y squared is less than or equal to 4. Do you recognize that? The equation x squared plus y squared equals 4 is a circle centered at the origin with radius 2, right? That's x squared plus y squared equals 4. If x squared plus y squared is equal to or less than 4, then we get this disk. Okay? Let's draw XYZ axes. What are you used to that being called in calculus? That's usually called R3, right? What does every element of R3 look like? It's not an ordered pair, is it? It's an ordered triple, where all three entries in the ordered triple is a real number, right? So it's the set of all ordered triples such that x is a real number, y is a real number, z is a real number. That's called a Cartesian triple product of R with itself. So that would be called R cross R cross R. Okay, but we just use R3 as abbreviation. Just like for R2. It's R cross R, but we just use R2 as an abbreviation. Okay? And you could do, you know, as high as you want. I can't draw it. I mean, technically speaking, I can only draw R2. But we can get away with depicting R3 by a drawing. It's not perfect, but it's pretty close. But anything higher than that, it's just impossible. But you can still imagine it. What about Rn? That's the set of all what we call ordered n-tuples. Now you might think I'm going to write x, y, z, and then what? I ran out of letters. So what people usually do is they write x1, comma, x2, comma, x3, comma, and it goes all the way up to, this is an ordered what? It's called an ordered n-tuple. So I stop at xn. That is an ordered n-tuple. Okay, such that, and now I can write x1 is an element of the real numbers, x2 is an element of the real numbers, x3 is an element of the real numbers, but it's a lot shorter for me to just write x, let's say I is an element of real numbers for every I from 1 to n. Okay, and that's Rn. And so what we just created is we created R cross R cross R cross dot 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 cross R. Okay, you can call that the Cartesian power is what our book calls it. Okay, the nth Cartesian power of R. That's what our book calls it. Okay, and this one that we just did a second ago, let me scroll back up. If you need to see that again, that I just written, and you can pause the video there. Okay, so that there, R cross R cross R, abbreviated by R3. I called that the Cartesian triple product of R. That's what most people would call it. You can also call it the third degree Cartesian product. Okay, this one here, R2, which is R cross R. Technically, that could be called the second Cartesian power of R. Okay? The Cartesian product of R with itself is the second Cartesian power of R. The triple Cartesian product of R with itself is called the third Cartesian power of R. And this one down here, where you take R n times and form the Cartesian product of those, that's called the nth Cartesian power of R. Okay, and you can do this with anything, not just numbers. Here's a nice example with dice. What if you were going to write down every possibility that you can get by rolling 2 dice? Okay, this is going to take some time here to write this all out, so bear with me. But you can roll. You know what I'll do for you? I'm going to pause the video and I'm going to draw this, and then I'm going to start the recording again so you won't have to sit through it. Okay, look at that. That's all 36 possibilities when you roll 2 dice, right? Okay, so here's what I want to point out. Look at the first die in each column here. These are all 1s. These are all 2s. 3s, 4s, 5s, and 6s. Okay, so what if we do this? What if we just take the set of all dice, okay, or I should say really the set of all 6 faces of a die. Let's call that D. Let's call that set D. Okay. Look again, I'll show you with these green arrows. Okay, now let's write that set D. Oh, look at that. A row disappeared, didn't it? Oh, let me pause the video and fix that, sorry. Okay, there we go, I fixed that, sorry about that. Okay, so there we have the set D. Now, I'm going to write that same set D along the left-hand side vertically. Okay, here we go. Let's put our commas in there. Okay, then look at this set right here. What is that set? That is D cross D, isn't it? Well, technically, if I'm going to write it that way, then I need to do what? I need to have my set brackets on there. And each element, which is an ordered pair, should be separated from the others by commas. Because that's how I write sets. Okay, so if you take the set of these 6 faces of a die and do the cross product with itself, then you get the set of all possibilities for rolling 2 dice. And that's the Cartesian product of D with itself. Okay? Alright, that was a short video, I know that. But that's okay, we'll take them while we can get them. Oh, one other thing before I forget. Yes, about the cardinality. This is important. If A and B are finite sets, like here, D is a finite set. There's only 6 elements in D, right? How many elements are in the Cartesian product of D with itself? You can just count them if you need to. How many are in there? There's 36, right? Why 36? It's because that is 6 times 6. If A and B are finite sets, then the cardinality of A cross B is going to equal the cardinality of A times the cardinality of B. That's only for finite sets. If they're infinite sets, then things can get different. Okay? All right, so that's all for today. Next lecture, we're going to start doing subsets. All right, have a good afternoon.